So I appreciate you guys joining me. In this session, we're going to talk about CQL, obviously. So if you're in the wrong room, you can go find the more interesting talk down the hall. This is not the sexiest talk that you'll see at this conference, but I feel like it's very important because I've talked to a lot of people in the last few years, and especially in the last couple of years as CQL has started to kind of take root, and read a lot of forums, answered a lot of Stack Overflow questions, had a lot of conversations where people call me and ask me, how to fix their problems. And what I've found is that we have this fantastic new way of interacting with Cassandra, which is CQL, but it still remains terribly misunderstood. And so what I hope is that in the next 45 minutes, 30, 45 minutes to help demystify that for some of you guys. So, because I think at the end of the day, there's actually a lot to gain from using it properly and not, if you may be one of the old people still using Thrift, I think there's a lot to gain from moving. So we'll get self-promotion out of the way real quick. I'm the software development manager at the Weather Channel. I work on the data services team, and my team is responsible for delivering back-end data, basically all the back-end data and analysis services for weather.com, the TWC mobile apps, and most of the other weather services that you use that you don't know you're getting from us. And so we actually provide weather data for the vast majority of weather-related services out there, whether you use iOS 8 or Google Now or Yahoo Weather, or a lot of these other services actually come to us as well. So we do about 10 billion transactions a day, which is not maybe Twitter scale, but it's significant. We feel like it's significant, and it puts us in a territory that not a lot of people are in. So, and I personally have been running Cassandra at scale, and my slides are miraculously moving on their own. I have personally used Cassandra at scale for 4.5 years, since the 0.5 release, and so that puts me in unicorn status, I think. So if you have any questions about how you can do things wrong, and you can come ask me, because I've done it every way you can do it wrong. And as a side note, I'm actually working on, this is really shameless promotion, I'm working on a book on highly available Cassandra, so if that's something that you're interested in, I'm actually really interested in hearing from people on that. So it should come out about next year, maybe not this time next year, but earlier, a little earlier than this, hopefully. We'll see. So anyway, if you're interested in that, come see me afterwards. So there are really two target audiences for this talk. One is people like myself, long-term Cassandra users who haven't yet adopted CQL, or they don't really understand it, and they may be, they may really be comfortable with the nuts and bolts of Cassandra. They don't really know what's going on with CQL. And I actually fell into this category up until about a year ago, a little more than a year ago at Cassandra Summit last year, when Sylvain, for those of you who were here and heard his talk last year on CQL, I found it to be compelling, and it caused me to take a second look. And so we have since moved, I think at this point, all of our services are using CQL instead of Thrift. So that says something. I'm in charge of Cassandra at Weather Channels, so the fact that we've done that says something when I was, poo-pooing it last year. So the other group, and I have my machine going crazy. So the other group is people who are new to Cassandra, and really you've never been exposed to anything but CQL. And, for these people, it's really important to be able to understand what's going on under the covers, because if it's easy to come from a relational background and see something that looks really familiar, and get sort of lulled into that. So I want to do a brief survey. Who here would say they fall into the first category? Long-term veterans, and okay, not very many of you. And of those people, I kind of got a quick survey. We maybe had 10 people. Of those people, who of you have switched to CQL? Okay, so it looks like. Okay, well that's good. So and the rest of you are holdouts. You're still using Thrift, I assume. So who falls into the second category? I presume that's everyone else. People who have not used anything but CQL. And then, so by show of hands, who in the room feels like they really understand what's happening with CQL? You guys are in the right place. And all of your friends who didn't make it to this talk, there's actually another talk that appears to be on the same thing later. So, which is, at first I thought that's, how did that happen? That must have been a logistical fail. But I think the topic is so important that I'm actually pretty happy that that's the case, because I think everyone needs to hear this. So let's start with some definitions so that we're on the same page. First, if you're new to the game, you certainly heard about Thrift. And this, I guess, will be helpful to a lot of the people in the room. So what is Thrift? Thrift is basically the old way of querying Cassandra. It's an RPC mechanism bolted onto a code generation tool that allowed us to talk to Cassandra in a sort of a language agnostic way. And then you had client libraries, all sorts of client libraries that would basically create language-specific idioms on top of that. So Thrift supported a set of lower-level calls to read and write data, as well as to perform administrative functions. The same things you do with CQL today. My machine continues to go to screensaver, and I'm not sure why that's happening. I apologize. And it's also advancing my slides. But that's okay. This is things that happen when you're standing in front of people that never happen when you're practicing, right? So I think I see what's going on now. Okay, so by contrast, the native protocol it's binary. It replaces Thrift, and it uses CQL by default. So there's a lot of benefits to using the native protocol, which I'll talk about in a minute. So if you want to use the native protocol and you want to use the new libraries, then you're essentially forced into CQL. I think that was probably not a mistake on the part of Ellis and crew. But so if you want to use the native protocol, you're going to be moving towards CQL. So there's an important distinction also between the storage layer, which is actually what all interactions prior to CQL were with the storage layer. The storage rows consist of partition keys and their corresponding columns. That's basically it, exactly as they're stored on disk. If you're a Cassandra veteran, you dealt with those directly. That's all that you understand. Whereas CQL actually introduces an abstraction layer on top of the storage rows. And it's really only a direct mapping to the storage rows in the very simplest of use cases. So unlike storage rows, which have no schema, CQL actually requires you to define a schema, but the data is still stored sparsely, so your null columns are actually just simply not there on disk. So let's do a quick history lesson. In the old days, as in a year and a half ago, we had lots of clients with a bunch of different APIs, like Hector, Astyanax, PyCasa, Pelops, Cassie, Aquiles, just to name a few. Depending on what language you're using, there were quite a few just for Java. The list is pretty extensive. So that meant we actually had no common language for talking about our schemas or queries. It was not uncommon to actually put a lot of investment in a given library only to see it abandoned. That happened to us a couple of times. So the Thrift API actually also had quite a steep learning curve, to the point that I actually used to advise people not to use Cassandra unless you really, really needed its features. And that's just simply not true anymore. So the other thing is Thrift didn't support cursors. And this may not seem like a big deal, except that you got a big data database. Everything had to be materialized into memory on both the client and the server. So this is a problem when you're dealing with lots and lots of rows of data. And especially considering that a bad query can OOM both your application and a Cassandra node. That's really bad. So that's one of its fundamental flaws. It's also hard to add new features because of the limitations of Thrift. And when new features were added, we actually had quite a bit of lag time between the time the feature would be added and when they would be adopted in the client libraries. So these are actually significant obstacles, and to me it's a testament to Cassandra and its capabilities that it survived through those days. So the solution, in my opinion, and in the opinion of the committers to Cassandra, it's CQL. So now we actually have a common familiar interface for communicating to and about our Cassandra data. But the reaction to this was probably not exactly what the developers intended. And I already gave it away because my glitchy little laptop here. So this was my reaction. As a matter of fact, as Jonathan Ellis has said in last year's keynote, many of us, like myself, were left saying, who put the SQL in my NoSQL, right? And at one point I even questioned whether Jonathan and crew had gone off the deep end. And maybe I should look elsewhere to a different database. But on the opposite front, now we have a bunch of new adopters coming out of the woodwork, and they think they can hit the ground running with what appears to be a familiar interface. So unfortunately, the reality is somewhere in between. Both groups need a reality check. For veterans like myself, there's no need to panic because CQL really is the answer to our Thrift pain, and it is painful, and you don't really know how painful it is until you stop using it. And we haven't really lost anything because the underlying storage is the same. Whereas for those new to Cassandra, which apparently is most of you guys in this room, CQL does improve the learning curve, which is substantial. I brought some new people online, and since CQL, and it's a lot easier than it was before. But it's not SQL. You still have to understand what you're doing, and no, you can't just index everything, right? So now that we've gotten that out of the way, let's peel back the onion a little bit and look at what's happening under the hood. So here's a simple example. We create a table called books with title as the primary key. We insert some data, and then we do a basic select. At this point, we could be looking at statements using MySQL or Oracle. It's basically just looks like ANSI SQL. So let's see what's happening at the storage layer. So the easiest way to do this is by looking at the old CLI, which is the predecessor to CQL-SH. And it allows us to interact directly with the storage rows. This is actually functionally equivalent to what we did in the previous slide. So we'll start by creating a key space, then a column family called books. And note that we don't actually have a schema we've defined. We simply tell Cassandra the types of our keys, column names, and column values, and then we start writing data. So while we're looking at this, let's remind ourselves about some key data distribution principles in Cassandra. First, remember that the key is assigned a random node using a hash algorithm, which is murmur3 by default, and that's the one you should use in case you're wondering. Do not use byte ordered, just as a little plug there. And the columns are, therefore the data is unordered. On the other hand, the columns are ordered naturally by name, as you can see here. Author comes before year lexicographically, so it's ordered first. So now let's look at a slightly more complex example. This time we have an authors table with a compound key and a short listing of the contents of the table. The question is, what does it mean to have a multi-part key? I think this is maybe one of the most misunderstood things in CQL. Well, when specifying a primary key in CQL, the first field is always the partition key, in this case, name. The remaining columns in the key are called clustering columns. So what are clustering columns? Well, they're simply values, they're column values that are sorted at write time in the order specified. So in this case, the data is actually partitioned by name, and then sorted by year, and then sorted by title. So for the old school people in the room, I'm going to show you what this looks like under the hood. Under the covers, this uses composite column names, which if you've been using Thrift, you most likely make extensive use of these. And since the column names are stored naturally by default, this works. So we can see here that this structure results in author name as the partition key, with the year and title stored as the first two parts of the composite column name, and where the column names are in sorted order. So we can also reverse the stored sort order by adding the with clustering order clause. The result, as you can see here, is what we would expect with 1993 coming before 1987. And again, this is what this looks like on the storage layer. And while this may seem to be a bit of a trivial point, it can be quite important depending on the types of queries you want to run. And so we'll look at it a little more closely later. We can also create a partition key that contains multiple parts, as in this example. The difference, in case it's not obvious, is the addition of the parentheses around the name and the year. So that leaves the title as actually the only remaining clustering column in this model. And the resulting storage layer representation, as you might have guessed, is that we now have a row key that combines name and year, and a composite column name that begins with the title. So we've essentially moved the year component from a component of the column name to a component of the key. So why should you care about any of this? Well, there are actually several reasons. First, your queries have to respect the underlying storage. Cassandra does not allow ad hoc queries like you can perform in SQL in a relational system. So if you don't understand how the data is stored, at best, you'll end up constantly frustrated by error messages that you receive. And at worst, you'll suffer poor performance. Second, you need to define your partition key properly because it must be known at query time. This is something that I see as a common point of confusion with Cassandra. It must also distribute well across the cluster. So something like a timestamp would be a bad key because it typically isn't known at query time. And a date is usually a bad key because you'll end up doing most of your writes to only a subset of your nodes. Third, because of its sequential log-structured storage, Cassandra handles range queries very well. A range query simply means that you select a range of columns being the keyword there, for a given key in the order they're stored. And lastly, you have to carefully order your clustering columns because this will affect the storage order of your data, and therefore determine the kinds of queries you can perform. So let's look at some examples of various queries using our authors table, with name as the partition key and year and title as clustering columns. We'll also reverse the sort order on year. So this is what our data looks like in CQL rows. So pretty straightforward. We'll start with a basic query by key. For all of these queries, we're going to assume a consistency level of quorum with a replication factor of 3. For this simple select, you can see that this query hits the coordinator node, which owns a replica for our key, and then it grabs the row from another replica node to satisfy the quorum. Thus, we need a total of 2 nodes to satisfy this query. At the storage layer, what happens is this query quickly finds the partition key using the hash, and then it scans all the columns in order to produce the result. So our simple query by key is actually a range query under the hood, and that's really important to sort of understand. So what happens when we actually do a range query, such as the one here? Well, in this case, we've added a query predicate limiting the year to greater than or equal to 1990. Again, we see it requires only 2 nodes to satisfy the query. Then at the storage layer, again, we find the partition key. That's going to be the first step in most of these queries. And then scan until the value is less than 1990. The important point here is that Cassandra only had to scan the columns we actually want, plus 1. The first time it hit a column less than 1990, it knew it was done, right? So again, this is because they're already sorted in descending order. So what if we reverse the query, asking for everything 1990 or older? Well, essentially, we're now querying the tail of the range instead of the head. So it looks the same, but then at the storage layer, it starts to look the same by finding the partition key. But in this case, we then have to scan the entire column range, and we filter out everything less than or equal to 1990. And this means we have to read a bunch of columns that we don't care about in order to get the ones we need. So depending on your data, this could be either trivial or it could be fatal. And now for one of the most common query errors I see, the end clause. Who in here uses the end clause? Who's afraid to raise their hand? So, what's happening here is we're actually asking for multiple partition keys in a single query. And so you might guess by now that, what happens is once the coordinator receives the request, it actually has to satisfy quorum for each key. And in our example distribution, this requires 5 out of 6 nodes to fulfill the request. It's easy to see how only a few keys in a large cluster can actually result in substantial overhead for this query, and actually poor availability as well. So in general, it's best to avoid using the end clause for this reason. So, what have we learned so far? We saw that if you want a fast query, it needs to be sequential at the storage layer because of its log-structured storage. And as a corollary, you want to always try to query by key and clustering columns because this results in a sequential lookup. We also noted that multi-key queries often result in lookups on many nodes. And lastly, you should always write in your intended read order. So those are some things that I hope that you've gleaned from that so far. So now let's move on so we covered some of the basic stuff. Let's move on to some more advanced concepts, starting with collections. So as a reminder, Cassandra supports 3 collection types. First is sets, which are unordered, or more accurately, naturally ordered, collections of items, and lists, which are ordered and allow duplicates, just like Java lists, Java sets, those sorts of things, and maps, which are key value pairs. So if you've been wondering where your dynamic columns went in your Thrift model, this is a good place to start. It works in some of those use cases. But we do have some caveats. The first being that we can only store 64,000 items in a collection, with each having a max size of 64K. So the second is that querying a collection always returns the entire collection. That's pretty important, especially if you have a lot of data. So the net result is that these are good for relatively small, bounded data sets. So let's look at an example of a set. Here we have a table of authors, with each author having a set of books. You can add and remove items from a set using an update statement as well. I'm only showing the insert here, but it does have update semantics. So at the storage layer, this is actually stored as a two-part composite column name. So the first part is the name of the set, and the second is actually the set item itself. So with this approach, we actually get, it sort of naturally disallows duplicates, because if you try to insert a duplicate, it simply causes an overwrite of the item. So lists actually look very similar at the CQL level, except that the curly braces are replaced by brackets, and the update syntax supports append and prepend operations to allow you to order things. So you can also see that when we query the list, we can see the list of books is in the order we specified and not in the natural order. You know, you can see Without Remorse obviously would come after Patriot Games if we were doing it in natural order. So unlike the set, the actual list item is stored in the value, since we want to allow for duplicates and we don't want natural sorting. Instead, each item in the list includes an ordering ID, and this ID gives us a way to exploit the natural ordering of column names while maintaining the order we asked for. Now on to maps. So you'll notice that the sort order on a map is actually based on the natural ordering of the key. Patriot Games comes ahead of Without Remorse. The map structure bears a strong resemblance to the list structure, except that the ordering ID is actually replaced by a map key. This prevents duplicate keys, as a duplicate will result in an overwrite, and it allows keys to be ordered naturally. So one of my favorite topics, indices. Who in here uses a secondary index somewhere? Only one person. Okay, well, I'm going to tell you now why you shouldn't do it in most cases. So at the beginning of the presentation, I said you can't just index everything. So let's take a look at what actually happens when you create and query an index. So here's a simple example where we're indexing the publisher column on the author table. Before diving into the details, let's remind ourselves of some important points regarding indices. First, they allow query by value in some limited circumstances. Some limited circumstances, okay? They are distributed based on the row key of the index table. This is really important, so we'll examine this concept actually a little bit more in detail in a minute. And updates are atomic, so you know when you insert an indexed field that the index is updated as well. And indices should be low cardinality, or they won't scale to large cluster sizes. If you're going to use an index, that's probably the most important thing to know. For example, birth year could make a reasonable index, but a UUID does not. But as a sort of corollary or opposite to that, we don't want extremely low cardinality like a Boolean or gender value. So let's look at how indexes are actually distributed across the cluster. Here we have 3 nodes in our cluster with 3 keys. Each key has 2 replicas. Using our publisher index as an example, you can see that the key of the index is actually the value of the index column, which is logical. But indices are not distributed the same way as normal tables, and that's maybe one of the most important things. If you're ever planning to use indexes, pay attention to these 2 slides. So you'll notice that the index only contains values for the keys stored on that node, okay? This makes sense because it allows each node to filter without having to perform a distributed join. And of course, what's the worst thing you can possibly do in a distributed database? A distributed join. So it prevents that. So now does anyone want to use indexes? So let's make it worse. So the index key distribution strategy has implications, right? So if you're going to query by value using an index, theoretically, the value we're querying could exist on any node in the cluster, right? We don't know where it exists. That's why we created an index. So its corresponding rows in the index table could live anywhere in the cluster. So what the coordinator has to do then, and does everybody know what I mean when I say coordinator? It's the node you talk, the node you ask when you send the request. So the coordinator, in this case, has to ask enough nodes to cover the entire token range. I'm not a PowerPoint guy, and I had to use PowerPoint for this, so it's biting me. So it has to cover the entire token range, which will involve many nodes, right? So in many ways, querying an index has a similar or even worse effect as using the end clause. So, and as a result, indexes should be used very sparingly, and they should not be a crutch for poor data modeling. Modeling data in Cassandra is different. It requires you to think about things. It requires you to write the data the way you want to read it. And indexing, I've seen a lot of times where indexing is just a crutch, where people, they didn't think about things in advance, so they just index everything. So that doesn't work in Cassandra. So if you started nodding off during that discussion, I can see a few of you, it's riveting, right? This is great. It's a lot of fun. So it's time to tune back in, because it's time to talk about deletes like this, right? You know that kind of delete, or that, a TTL, right? You're familiar with those, but what about those? Okay, nulls. Who in here knew that inserting nulls caused a delete? One guy, two guys, three guys, four people. 4 people in the room knew that. Yeah, inserting a null causes a delete. So let's remember about deletes in Cassandra. Cassandra uses a log structured storage engine, which means that writes are immutable, right? So if writes are immutable, you can't actually delete data. So you have to add a marker that says, hey, ignore this column. That marker is called a tombstone. And you get 1 for each column you delete. So, and in order to make sure it doesn't hand you deleted data, Cassandra has to read those tombstones and remove the affected records from your result set. Because of this, deleting data in any significant volume is an anti-pattern. Did everybody hear that? Do not delete data in volume on Cassandra. So there are very unusual cases where it can be okay, but if you don't already know what those are, then don't use those. Don't use it. So to drive this point home, let's look at the difference between columns that are simply missing and deleted columns. As previously discussed, data is stored sparsely, so missing columns simply are not written. When you query using CQL, missing columns appear as nulls, but really, in reality, they just aren't there at all. So we can see that in the storage layer representation there below. So if we turn on tracing to see what's actually happening, we can verify that we just read 1 column to produce the result. This is actually, if you haven't used tracing, this is a fantastic way to find out where you have issues with your queries. So Cassandra, in this case, actually didn't need to reconcile any tombstones. So this is really important. If you ever do deletes, you should monitor this and trace your queries to find out what's happening. On the other hand, what if we actually specify null values for our ISBN and publisher in this model? Well, as we just discussed, this is going to result in 2 deletes. So the question comes, why can't Cassandra just not write those values, right? I specified nulls, why can't it do that? Well, the reason is because inserts and updates are basically the same in Cassandra. We get, the CQL syntax puts some dressing over that, but if you use the Thrift API, you know that everything's just a mutation. So there's really no difference between inserts and updates. It's giving away my secrets. So, and since Cassandra, so what's happening is they're both just writes on the commit log. So Cassandra doesn't read before it writes. That would be catastrophic, right? So it has no way to know whether there were previously values written for those columns. So it must write tombstones just to make sure. So we can actually verify this by tracing our query. Sure enough, we read 1 live cell, but 2 tombstones, and that was 1 for each null that we wrote. This equates to 3 total reads for only 1 column that we were actually trying to read. So at small volumes, this might be all right. You might not even notice it, which is why this has a tendency to appear in production, right? And not in development, and why you should always load test. But it can get really out of hand if you're dealing with large amounts of data. I have seen this get out of hand with the TTL case, where people are using TTLs, and they don't realize that every time they read their data, they're actually scanning large amounts of tombstones. I've seen people actually exceed the number of allowable tombstones in a query for this reason. So it also means you need to be careful when using, listen for this part about deletes. Prepared statements. This is where you can get in trouble. Prepared statements with a bunch of columns you may not need. This is a common usage pattern in like JDBC type work, right? You create one prepared statement, you just populate the columns you need, right? Because it doesn't matter if you write nulls. It does matter. So it's better to prepare multiple statements that actually cover the permutation that you need in that case. So let's talk a little bit about why queries fail, maybe a little bit more slowly than my slides are going. So I suspect, wow, look at that. So I suspect that one of the reasons you decided to come to this talk is because you wanted to get the name of the author who wrote Patriot Games. That's why I came. So, but you asked Cassandra to tell you, and you got this, right? Primary key part title cannot be restricted. Preceding part year is either not restricted or by a non-EQ relation. So for the love of Oracle, what does that mean, right? To answer this, let's look at some of the reasons why queries fail. First, if you don't provide the full partition key, in most cases, you're going to get a nasty response. Cassandra needs the key to know exactly which one of your 100 nodes owns the data where it lives on disk. Second, you might be trying to query by value as you would in a relational database, but you actually haven't created an index on that value. Without an index, querying by value would result in a full table scan. And if you have terabytes of data, this is a bad idea, right? And Cassandra simply doesn't let you do it. And lastly, the other possibility is you're confused about how clustering columns work. But don't worry, I'm going to try to resolve your misunderstanding. So let's go back to an earlier example where our authors table had a compound partition key, name and year. If you recall, this resulted in a storage layer representation that looks like this, with two parts of our key acting as the row key. So what happens if we try to do a select specifying only the author's name? Well, as we should expect, it fails with this horrible error message that ends in is, because we only supplied half of the partition key. Cassandra is unable to locate the data without the complete key because it can't compute the hash. The same thing happens if we try to filter only on year, except that the error tells us specifically that the name must be restricted as well. It's a little bit more helpful. Interestingly, attempting a range query on year gives us the same message, which is a bit misleading because it implies that maybe we could just add the name part and get what we want, right? But if we do this, we see that no. In fact, we can only use equals comparisons on the partition key parts. This is because, if you will recall, the keys are randomly distributed, making range queries impossible unless you use byte-ordered partitioner, which doesn't exist as far as you're concerned. And don't get too excited about the token function, which is referenced in this error message, because it doesn't solve this use case. The token function allows you to get the hash token for a given key and is useful for paging through your entire table. It does not permit range queries on partition keys, so don't get excited. As we've discussed, Cassandra doesn't allow us to query by value without an index. So if we do, as in this example where we're asking for authors with a specific ISBN, we get an error indicating we haven't specified an index column. So the solution is in fact not to create an index, it's to create a sane data model. So perhaps the greatest source of query confusion is actually with clustering columns. This is probably because many people don't understand how they're stored, which we did look at, and so hopefully you do now. And giving my things away again. So they don't realize that Cassandra limits you, and this is important, if you don't get anything else from what I've said, Cassandra limits you to mostly queries that can return contiguous data without filtering, okay? So once you understand this, queries involving clustering columns make a whole lot more sense. So let's go back to our authors table, except this time year and title are clustering columns. So year is no longer part of the partition key. And let's remember what this looks like at the storage layer. So we have our clustering columns translated to composite column names, right? And so let's look at some possible queries. First, we'll do a select using the partition key, because now we know we need it, right? Everybody knows that now. And then we'll filter on year. This works because it's a simple range query, okay? And so this is what it looks like, again, it's a small range, but in this case, it's still a range. It's 2 columns in order. And specifying a range of years also works for the same reason, right? Because under the hood, it's just starting at 1 year and going to the next in order on disk. So we already know that Cassandra won't tell us who wrote Patriot Games, unfortunately, because we have to tell it the author's name. But what about a query based on name and title, like this? Sorry, can't do that either. For that same error message. And the reason is because it would have to scan the entire row to find the relevant columns. Now, in this example, I have Patriot Games only listed once, but there's absolutely no reason why you couldn't have it many times in your data. And so the only way to find it would be for it to search all of the rows in order for it to locate Patriot Games, because it's the second component of the key, of the column name. There could theoretically be millions of columns in this row, so Cassandra won't let you do this. So now here's an interesting example. We do a select without providing the partition key, and instead we ask for a specific year, which is the first clustering column. Based on what you've already learned, you'd think that Cassandra would simply disallow this. Well, sort of. The error it returns tells us that this is probably a bad idea, but we can do it anyway if we use the allow filtering clause. So let's just do it, right? Sure enough, adding this clause lets us run the query and everything seems fine. But this is because we don't have much data in our table. And in fact, this query requires a full table scan to locate the columns where the component is equal to 1987, where the year component. If you know you're querying a very small table, such as a lookup table, this could be okay. If you know for sure that you have authors who wrote books in 1987, one way to potentially mitigate the damage of allow filtering is to add a limit clause. This has the effect of scanning only until you hit a column or columns that match your criteria. However, it actually doesn't protect you from the worst case scenario in which you have no records matching the criteria, or if your limit can't be satisfied. So that would actually result in a full table scan. And I'm going to finish up here so I can get some questions. So the bottom line is Cassandra wants you to query sequential ranges without filtering. And that's because it's designed to handle huge amounts of data where random seeks and table scans are a bad idea. So think about your queries in that way. So to sum up, so we can get some questions, let's remember 2 things. 1, Thrift is dead. Switch to CQL as soon as possible, but make sure you understand your data models and queries, because it's not SQL. So thank you very much.
Thank you, Robbie.